Hello, so today we're going to be talking more about electron configuration, more specifically how to write it and how to write electron configuration correctly for elements. So we'll just dive right into it. So a couple of principles that we need to really evaluate before going into the specific writing rules. The first one is called off-bound principle. It states that electrons always occupy the lowest energy level first, which kind of makes sense, right? I mean, they want to be in the most stable position as possible, which typically means lower energy. Electrons or anything does not want to be in more higher energy than it's supposed to be. So based off that, they want to again occupy the lowest principal quantum number first, which we know is 1. So it wants to occupy orbitals that have the lowest quantum number first. So it also states that electrons will want to completely fill the lowest energy level before moving on to the next energy level. Again, I mean, we know that the lowest energy level is 1. We know that's an s orbital, so the s orbital can hold 2 electrons. So there has to be at least 3 electrons before another energy level can be accessed within an atom. So suppose I have one orbital at one level and another orbital at another level. So I would call this 1s1 because this is a 1s orbital with 1 electron in it. Now before I can even dive into the next one, this is not true, right? So I want to take that out, and then I would want to pair the electron in the lower s orbital first. And now this becomes 1s2 because it's a 1s orbital, the lowest quantum energy, lowest orbital with 2 electrons in it. Now that I have 2 within that position, then I can move on to the next one, which is 2s1, and if I add another one, it becomes 2s2. Pauli exclusion principle states that each orbital can only occupy 2 electrons, and the 2 electrons must have opposite spins. Okay. So this is the very important rule. So each line that you draw, that orbital position, can only have 2 electrons. And for them to be stable, they have to have one going up and one going down. So for an s orbital, there's only one electron position. There's only one type of orbital. There's one sphere that it can occupy. So there has to be one electron going up and one electron going down. So the total number of electrons within that can be occupied in the s orbital is 2. Now p, if we go back to the previous video, we know those are the dumbbells, and they have 3 different positions that the shape can be in. So there can actually be 3 orbital positions that electrons can occupy, which means that if I count these up, I can occupy 6 electrons within p orbitals. But again, each orbital can only contain 1. So one line, one orbital. So if this was the dumbbell on the x-axis, it can only hold 2 electrons, one going up, one going down. This would be the one on the z-axis, and this would be the one on the y-axis. So a total of electrons that can occupy a p orbital is 6. D, again, has 5 different shapes it has, so that means it has 5 different orbital positions, a quantum number of 5, okay? Quantum number of magnetic quantum number of 5, and which means I can put 2 electrons into each one of opposite spin, and I have a total of 10 electrons that can occupy a d orbital. And then F has 7 positions because there's 7 funky shapes. Each position holds 2 electrons of opposite spins, so therefore it can hold a total of 14. So another way you can kind of look at this, if you want to put in more of a table form, if I say the type of orbital is S and it has only 1 orbital position and it can only hold 2 electrons per orbital, the number of electrons times the orbital positions is equivalent to the total number of electrons that that orbital can occupy. So 2 for S, 6 for P because 3 times 2, 10 for D, 5 times 2, and 14 is F, 7 times 2. Hund's rule. Now this one's a little bit weirder, but it states that no pairing of electrons can occur within p, d, and f orbitals until each orbital position has at least 1 electron. So no pairing wants to occur until each orbital is filled with at least 1. Again, because that's why the electrons want to spread out as much as possible to be at lower energy states, because when another electron comes in, even if it's at a opposite spin, there is still some conflicting there. So electrons want to spread out as much as possible, be on their own as much as possible, unless absolutely needed to. So if we look at a p orbital, we do the 3 orbital positions. If I was filling the p orbital up totally, the way you would write this out is that you would draw the first 3 lines, and you add the first electron, the second electron, and the third electron, where each orbital has 1 electron spinning up. And then if you had more than 3 electrons in the p orbital, then that's when you would start adding the additional ones. Okay, so this would represent a p6, 6 electrons within a p orbital. D, the same thing. You have 5, so if you have 5 electrons, you would fill each one up with one first. If you have more than 5, then that's when you start adding them back in the opposite spin. And then add the exact same thing. So you have the 7, add one up, all the way up to 7. If you have more than 7 electrons within the f orbital, then you start adding in opposite spins. All right, so to write the correct electron configuration notation for an atom, you really just need to be able to read the periodic table from the left to the right. How do we read it? Well, I'll give you an example. So suppose I want to write the electron configuration for a neutral atom of carbon. Let's take a look at the periodic table that I created in the previous video to help identify what's going on here. So first question I ask myself is, where is carbon? Well, if I look at the periodic table, it's right about there. Okay, so it's within the 2p block. So we know from the previous video that it's going to end with a 2p address. Okay, so that's second block on the 2p row. So the first rule you want to do is you always want to start with the lowest energy level orbital, which we know 99% of the time, pretty much 100% of the time, 99% being further advanced science, is always going to be the 1s orbital. It's going to be the 1s orbital with some number of electrons in it. Okay, so x meaning the number of electrons occupying that particular orbital. Second is to find where the notation is going to end, so the end of the atomic or the element address. So if I go back to the carbon example, if I look back at the periodic table, I know that carbon is the second block in the 2p row. Each block on the periodic table represents one electron. So if I have 2 blocks in the 2p row, that means that the ending address of carbon is 2p2. Okay, so now the address looks like 1s2 because I have to fill the 1s orbital up to even move on to the second row, which I know carbon is in, and it's going to end in 2p2. So now I just have to figure out what's in the middle. So we look back at the periodic table and we say, okay, what's in the middle of the 1s and 2p orbitals? Well, we know it's the 2s block. Okay, so we know that it goes 1s1, 1s2, and we know it's going to end in 2p2, so now we got to finish it off with the 2s's. So we count the element blocks starting from H, so we start at hydrogen, and then we make the following inference. We say, okay, we count across, we know we crossed the 1s, there's 2 element blocks in the 1s, which means there's going to be 2 electrons in the 1s, so there's 1s2. And then I count to the 2s blocks. I know there's 2 element blocks I'm going to count, and that means each element block has 2, so that means it's going to be 2s2. And then I get to the 2p block, and I only count 2 blocks in because that's where carbon is. So each element block is 1 electron, so for each element block there are 2 occupying electrons, so it's 2p2. So a neutral carbon atom where it's equivalently charged both positively and negatively, it's not an ion or anything like that, the configuration for carbon is 1s2, 2s2, 2p2. So how do we know the answer is right? Well, we can access our knowledge of atomic structure. So we know that a carbon in a neutral atom that's not an ion, that means it has a correct number of electrons to negate the positive and electric charges to not have an overall charge of 0. It has not gained or lost an electron. So the number of electrons must equal the number of protons in the atom. Well, we know that the carbon's atomic number is 6 based off of what we read on the periodic table, which means it has to have 6 protons in its nucleus. Well, for it to not be an ion, that means that carbon has to have 6 electrons. So we just look at the electron configuration again. We say 1s2, 2s2, 2p2. We know that the superscripts equal the number of electrons in each of those orbitals, so we just add them up. 2 plus 2 plus 2 is 6. Okay, so I have 6 electrons in my electron configuration, which means I have a neutral atom of carbon. That's equivalent to the atomic number of carbon, which is also 6. All right, so a little bit shorter of a video too. If I went too fast for some reason, feel free to come talk to me. But it is stuff that you're going to want to start catching up on. You're more than welcome to watch this video, pause it, and everything that you need to. If you have any further clarifying questions, come talk to me or email me or anything like that. But thanks for joining me, and I hope to see you in the next video and see you in class. Bye.